morning. Let's start. People are still coming in, but so it's my pleasure to introduce the third day of our workshop. So today we have Erik Luijten, so we invest him as a keynote speaker. And just a brief plan, it's going to be the same as the rest of the days. So we will have a keynote speaker in the morning, and Michael Fogg is here, and he will tell you something about the research here. We have lunch, photo is 12:45. Don't forget, you can go outside. And then we record a workshop in the afternoon. Okay? Of course, our sponsors. And thank, of course, Corey and Brandon for moving on everything. Survey, we can do the survey later. We'll do the tutorial. So let me just introduce the speaker. So Erik Luijten, he was my postdoc advisor at Northwestern. He's a professor at the Department of Material Science and Engineering at Northwestern University. He did his undergrad and PhD in the Netherlands in physics, and he worked in Germany with Curk and University of Maryland College Park with Michael Fisher. He was an assistant professor at University of Illinois at Urbana-Champaign and became associate professor and then moved to Northwestern since. He has won many awards. I'm not going to go into that. He's an expert in computer simulations, particularly of soft matter systems. And he will tell you something. Without further ado, thank you.
All right. Thank you, Tine, for the nice introduction, and thank you all for being here. Also, thank you to the organizers for inviting me to this workshop. So I have a great passion for simulations, and I hope to show you today the cool things that we can do, you can do. So my long title says, I really want to talk about combination or combining computer simulations with experiments. And it seems a very natural thing to do, but strikingly, I would say that many experimentalists don't appreciate the value that simulations can bring. And many people who like simulations do not make the effort to speak the language of experimentalists. And that's the only way it will go. You will rarely find an experimentalist who is going to dive into the nitty-gritty of what your simulations can or cannot do. And so what I want to show you today is really a number of examples of where a lot of progress can be made, has been made in understanding collective phenomena. So really material science, sometimes crossing into physical chemistry and physics. I mean, boundaries are very blurry. Of situations where you cannot understand the system by just looking at a small number of particles. Despite what Tina asked me, I will not go into the nitty-gritty of algorithms. Not because I don't care. I actually love that, standing for 2 hours in front of the blackboard and just discussing, what you should do here or there. But as you know, time just evaporates at that moment. So I'm around for quite a bit of the day today. I'm happy to talk more, your lunch or whenever. But I really want to emphasize where one can get with the simulations themselves without going into, as I said, the details of the simulation. This slide will not dwell on it for too long, but it's really to give you an idea of the sort of things that I've been interested in the last few years. I have a very strong interest in colloidal self-assembly. So let's say 100 nanometer to micron-sized particles. And as soon as you start working on that, there's so many different things you can do. Not only in soft matter systems, but well beyond that. So actually, I was asked to write a review article with my collaborator, Marjolein Dijkstra in the Netherlands for Nature Materials 3 years ago. Had some other Tina, you were on this paper, I believe, right, in Nature Nanotechnology last year. Have a very strong interest in dielectric materials. So systems, and I will talk about that, where materials with different permittivity meet and what are the consequences of that. Hierarchical material self-assembly is something that's still developing because it's spans so many length scales that it gets very complicated. And over the last few years, also I've developed a strong interest in systems in which you have explicit hydrodynamics. If you're only interested in thermodynamic equilibrium, you can typically leave out the hydrodynamics, which makes everything much faster, and say, well, I don't care how we get to this state, that I can predict the equilibrium state without representing the solvent. But many systems are, of course, not in equilibrium, and then the state that you will observe depends on the pathways you take, and then hydrodynamics matter. So, what is the real challenge in simulation? So, as soon as you go to soft materials, systems tend to contain large particles with very different sizes, systems that evolve very slowly. Everything has to become like coarse grains, so that means your answers automatically will be approximate. So it's extremely different from, let's say, understanding, let's say, crystallization of iron, right? Where you have these atoms that are very simple, go into a very simple structure. You can put it nowadays on a computer. You can download LAMPS, which is very widely used MD package, and get this going, before the morning is over. But it's not like that in systems, in soft materials. So the question is then, all right, given all these approximations, can you actually make any useful predictions? Can you even make it somewhat quantitative? So what is actually the contribution that you can make? And so I really want to dwell on that. The other thing I want to note, because I think that in the last few days you also have DFT and other topics. Great, I have nothing against them whatsoever, but there's one particular point where particle-based simulations are really amazingly helpful, and that is in systems where entropy is, let's say, as important as enthalpy. Human intuition is very naturally inclined to understand anything that's enthalpically driven, right? I mean, if I just drop this pointer right now, then gravity pulls it down, and that's obviously purely potential energy driven. But the air molecules here don't do that. No, why not, right? So that's obvious that entropy plays a role there. And human intuition is much worse than that. And so that means that on the one hand, you need simulations that explicitly incorporate this. And on the other hand, it also means there's a lot of room for exciting discoveries, counterintuitive discoveries. So it's always fun. So I want to start with a project that stems from a current collaboration I have with Chen Chen. She's a professor at U of I Novella-Champaign. She worked with Paul Alivisatos as a Miller postdoc in Berkeley, because Alivisatos now is president of U of Chicago. And her expertise is in liquid phase TEM. So the one thing you need to know about this is that if you want to study self-assembly of particles that are so small that you need TEM, so confocal imaging will not work if your particles are, let's say, 100 nanometers or so. This self-assembly, if you do not just want to see the result, but you want to see the process, you need to have this take place in water. Sending an electron beam through water does not work well. It attenuates very quickly. Natural inclination might be to crank up the intensity of the electron beam. This is a really bad idea because you're going to ionize water like crazy. And so then everything changes. So instead, now people make these very thin cells, maybe only 100 nanometer or so. No, that's not true. But I'm exaggerating there. Let's say maybe few micron in width, I would say. So then the electron beam goes through a very thin slice of water, doesn't get attenuated too badly. You don't produce too much salt, so H plus and OH minus. And you can actually monitor self-assembly processes of nanoparticles in real time. And so that's kind of cool. And I should say in real space, right? Because normally if you go to particles that are this small, then you start thinking of X-ray, and then of course everything goes in momentum space, which means that it's a very different image that you get of the process. So to demonstrate that we really can now see things that you couldn't see before, we developed a model system. And so we have these triangular nanoprisms, which are here at the bottom left. So because they have strong van der Waals attractions, they aggregate very quickly and get something amorphous. To avoid that, they are coated with ligands that are charged. And so she started looking with her group at what happens in the system. And so what she saw, to her surprise, and maybe also to your surprise, is not a triangular lattice, which is what normally you would expect. If you have triangular particles, they should expect some sort of like triangular lattice, but instead they go into an hexagonal lattice. So we developed computer simulation. In this case, it's a Monte Carlo simulation. And first thing to note here is these particles are so small that you can actually get pretty close to a decent prediction of the true particle-particle interactions. Because you can essentially imagine this particle buildup out of like atoms, gold atoms. You know the van der Waals attraction between gold atoms, and you can just sum between all the atoms, all atom pairs between the two particles. But it's still challenging because if I give you a triangular particle and I say, well, two triangles are meeting, then of course that is very different from two spherical particles are meeting. In what orientation are they meeting? And so it's still pretty complicated, but we were able to develop an effective potential between every pair of these nanoparticles, put it in a Monte Carlo simulation, and we saw the same thing. That's already good. So in this picture, this is actually a true image from the simulation. There are two things that you need to see. So there is this projection here that my student Ziwei created, so you can already see this looks kind of like an hexagonal lattice. Then the color coding indicates this psi6 order parameter. That's an order parameter designed to detect hexagonal packing. And so the more red this order parameter is, the closer you are to an hexagonal packing. So very similar to what you see on the right. So that's good. The question, of course, is why? And so the answer lies into, indeed, a combination of enthalpy and entropy. The attraction brings the particles together, they stack with their surfaces on top of each other, but because they also are charged, or the ligands are charged, they want to not completely maximize their surface area. So it's not like two triangles stacked on top of each other directly, but the second one is rotated with respect to the first one. So you get a sort of Star of David-like motif. And that continues throughout the stack, so you get basically a stack of triangles that is disordered in terms of orientation. And that means that the effective circumference of this stack is a cylinder. And of course, when you have cylinders, then you completely understand why you get hexagonal packing. To illustrate, well, okay, that's a little toy system, and why should I care that much about this? The cool thing is now that we can illustrate that this liquid phase TEM in combination with the simulations can give you insights. So we can now see crystallization, nucleation, and growth of nanoparticles in real time. Yes, you can say I could have done that with colloids, micron-sized colloids. Life would have been simple. You could have just used confocal microscopy. The big difference is that colloids have been advocated for years, and I believe this as well, and maybe even have advocated it myself, a great model system for atoms, right? Because you can see them, it moves on the scale of seconds to minutes. It's all great, and you get beautiful crystals. The issue is this: if you actually look a little deeper into what is the interaction between a pair of, let's say, any type of atoms, and how does that compare to their size? That range is maybe 50% of the size of the atoms, maybe even more. If you go to colloids, let's say a micron-sized colloid, the interaction range is maybe 10 nanometers. That's 1% of their range. So they behave very differently. They don't feel each other until they're very close, and then they stick. Nanoparticles are much more similar to atoms in that regard. And of course, we have the bonus that with nanoparticles, we can actually tune the interaction quite easily. So much better model system for atoms, but at the same time, it doesn't behave crazy fast like atoms do. And of course, the scale is accessible. What's cool here, if you look at the bottom row, you see that there is x and a y-axis. So the x-axis is the order parameter in terms of hexagonal packing. The y-axis is the density. So what we find is, and so every system is, the images look like this, right? So you say, oh, they look kind of fuzzy. This is on purpose. It is very easy to get tempted in getting beautiful TEM images by cranking up electron beam intensity. Sure, it looks great, but it fails within no time because you're creating so much salt. And then you change the interaction between the particles. So instead you have to just, retain a certain modesty and said, okay, these images are maybe not that impressive to the audience, but we know where the particles are, and that's the only thing that matters. And in exchange, we don't contaminate the system. So we can see what's going on. And so we classify these images. And so here you see at the bottom row, this time evolution. Initially, the system densifies. So you get dense clusters of particles, but they are still disorganized. So that's, let's say you go from a gas to a liquid state. And then over time, you see that that intensity map here shifts to the right. And you start, after 100 seconds in this case, you see that you start to get systems or parts of the system that are not just dense, but they're also hexagonally ordered. So that's a very nice illustration of how crystallization happens. You first form dense clusters, and only once these dense clusters have formed, they start to organize into a crystalline structure. So if you start thinking about crystallization, then you realize, oh, there are tons of other systems. And so this slide illustrates a paper that Tine was a co-author of. Here we take nanoparticles, and when I say nanoparticles, you have to think 80 to 100 nanometer on the side. It's kind of the smallest we go to. Again, we map the potential very accurately, put it in a simulation to understand crystallization now of cubes. They can be either regular cubes or cubes with little dimples on their faces. You look at spheres. And the cool thing is now that somebody asks you, okay, how do thin films grow? And you go to the literature, and this is material science from 100 years ago, right? This is like layer by layer growth and things like that. And effectively, the picture is particles are raining down onto a substrate, and then they move around. And if there's a little island, the particles fall off the island, and so on. So very intuitive. But if you then ask, okay, so to what extent has that actually been seen? Then there is much less than you might think. And this really depends strongly on the interaction range. If you have, let's say, a little cube that's sliding on this table, and it needs to fall off the table to, extend this layer that is formed by the table, it really depends on what the interaction range is. Because at the moment that something drops off a cliff, it is temporarily more or less detached from the island. To which degree it's detached depends on how long the range the potential is. So this is where colloids that you could be studying are very different from the atoms that we are interested in. So these are the still images here on this slide from the observations, but you can see that we can actually track particles sliding back and forth, and even for nanoparticles, and even with all this sophisticated technology, that's pushing the limits of what we can do, because the resolution of the TEM cameras, the latest generation, the company is called Catan, it's like K2 and K3 cameras, very expensive. They still have like millisecond resolution at best. And so if you actually check the rate at which particles are moving when they have this size, then you're really pushing it. If you see milliseconds, then the particle might have moved quite a bit before you take your next image, but still, you can see what's happening. We can characterize the growth of the individual layers. And so that's very informative. And so doing the matching simulations, we realized, well, it really depends on how fast particles are raining down compared to the rate at which they are moving on the substrate. And theoretically, it's easy to see that there should be quite a few different regimes, in fact, 4 different regimes. And if you go into the literature, you realize that some of these have been seen a lot, others have barely been seen. They're like occasional reports. in this nanoparticle system, because we can tune the particle's shape, we can change the interactions, we can actually realize all these regimes. And of course, in the simulations, in this case, we do kinetic Monte Carlo simulations in which you simply assume that particles appear on a substrate and then move around. We can show that, let's say, the phase map can be described by, on the one hand, the rate at which the particles rain down compared to the rate at which they diffuse laterally. And on the other hand, it's controlled by the range of various interaction parameters between the particles. And so, because time is a little bit tight, I want to talk about a lot of different topics today. I will only show you that the surface morphology, so the color coding here tells you the number of layers that you see at any location in a top view of the surface. The morphology really is qualitatively different for different settings and bring you into this in this map. So colloids are typically here, atoms are here, very different, right? So these are two different regimes. And nanoparticles can span a whole bunch of regimes. So we can see those in real space, real time, and in the simulations we can explain all the morphologies that appear. And so in a way, it's also once again a reminder that colloids are not a good stand-in for atoms. All right. So this was about dynamics, but still dynamics toward equilibrium. If you now go to larger molecules, you can even forget about that. So you will typically end up in situations that are kinetically trapped. So particles that have met in a certain way, and they just stick there now because the attraction is so strong. And at first sight, you might say, well, yes, so then it's probably something random, right? Like glass, any amorphous material. It turns out to be not true, and in fact, your own bodies are an evidence of that, right? Completely out of equilibrium and yet very organized. So, because in biology, there's a lot of hierarchical creation of materials, and I think bone is an extreme example of this, and there's not enough time to really dwell on it, but the amazing thing is that bone has length scales, so of organization that start on the nanometer scale and go to almost a millimeter scale. Different structures, so layer by layer has a different structure. And I say layer by layer, I mean length scale upon length scale. Absolutely amazing. Synthetically, we are nowhere near being able to make stuff like that, right? With that sort of organization. And so the question is that even the beginning of making hierarchical structures that are dynamical in experiment and explain what's happening with computation. So in this case, I worked with Sam Stuck. He is a distinguished faculty member at Northwestern, works on biomedical engineering, material science, chemistry, medicine. And Renette Freeman, she was at the time his postdoc. She is now a professor at the University of North Carolina. So I'll just take you through this really quickly because it's kind of clever. So take peptides. The peptides themselves have a head and a tail, so it's kind of like a micellar structure that forms, right, where the hydrophobic tail is on the inside, the hydrophilic parts on the outside, so you get this cylindrical micelle in a way. But now they did the following. They attached short strands of single-stranded DNA onto these peptide groups, but only on a small fraction of them. If you do that, and now that the self-assembly proceeds, then you get these cylindrical micelles. Think of them as chains with single-stranded DNA sticking out. If you now have a bunch of these chains, then when they meet, complementary single-stranded DNA will match and create a bond between these cylindrical micelles. And now you can think of this as a gel that you've created, right? Because you have these tubes, they're somewhat flexible, mega polymers, you could think, right? Although they're really supramolecular, right? Because they're made out of individual peptides that are then cross-linked. Okay, that sounds like a really complicated way to make something cross-linked. But the cool thing is that I think 10, 15 years ago, the technology was conceived, very clever, I would say, where you can break these cross-linked DNA pairs. And you do this by adding a third type of single-stranded DNA that actually binds more strongly to one of these two that are already bonded. You think, oh, how is it possible? Oh, because it's simply a little longer, and so there is the red and blue, they don't completely match. They match to some extent, and the green matches over a larger length to the red. So that when the green is inserted, the red and blue will unbind, the green will bind to all the reds, and so then you have now unzipped, so to speak, all these links, and you've gone from a gel back to a liquid. And the little images from the experiment show that indeed the color confirms that this is happening. So, what do you get? Under electron microscopy, now you see that you get this cross-link structure, this purple gel, okay? But on top of that, you get these huge bundles. And I want to emphasize that if you now simulate it, you think, oh my goodness, how can I possibly get started with it? Because if you take a closer look, you realize this is what you're looking at. So one of these bundles contains thousands of these supramolecular chains. To remind you, each of those chains is self-assembled out of peptides. Right, so this is like, there's so many length scales going on. This thing is humongous. And then on top of that, they found, and this was really the clue, that this, of course, you're artificially covered, right? It's simply the Photoshop, to be sure, right? So the pink, indicates those bundles, which interestingly are somewhat twisted, and the DNA turns out to be mostly found in those bundles, not so much in the purple background. Well, there has to be some because it's cross-linked, but a lot of DNA has migrated. So this is where simulation can contribute. Now skip this. We make the following model. We have to make this as simple as possible because we realize this is going to be slow to evolve. So better make the individual building blocks simple. So we did something that is very simple. We created these fibers, and if you're not interested in the nitty-gritty of the MD, this is a standard MD simulation. You simply make spheres that are bonded, like you would make a polymer, but the bond, the length between the spheres is very short compared to the diameter of the spheres. Very different from what you normally would do. So now you get this sort of like, yeah, it's like a little caterpillar almost, right? So it's like all these overlapping spheres forms this sort of worm. In fact, the dots here tell you how close together the spheres are. Then to the center of some of these spheres, we attach a little chain that sticks out of the sphere, which represents the DNA. We make it very simple, right? So there's like some pattern, yellow, green, blue, and here there's something yellow, pink, red, and we then make rules who bonds to whom, so that we get this selective pairing of red and blue. And then we set some other potentials to make these things very stiff. Yeah, flexible, but only barely. Put that in the simulation. And at that point, it got a little scary because this is done by my student, Ming Han. He just started now as an assistant professor in China at Peking University. And this is simulation what you get after running on, let's say, 48 cores or something like that, fast cores too, for like 3 weeks. And you know nothing until the simulation is done. So that's a bit like, okay, might be a big disappointment. And indeed, it was a bit of a disappointment because we get this gel, okay, that's cool. The purple and red, which you can barely see, are the DNA pairs. Yeah, you get a mess, you get a gel, that's fine. I could have kind of guessed this, right? But it's not what we wanted. We said, well, how could you get anything else, right? Can you think of anything that might have happened? And we realized, the DNA is non-uniformly distributed. And that's not possible for us because the DNA is just stuck to these chains, these polymers. Let's make those mobile. Give them a chance to move. There's some, that allow them to have some attraction to the beads, but they can move out. Do same simulation, submit to our, supercomputer at Northwestern, pick up the results after 3 more weeks. Boom. So we are, of course, super excited. when this came out of our visualization. So now you see that indeed these bundles form. It means that's one of those situations where the simulation, with indeed some luck and some creative thinking, tells you why did this happen. But on top of that, it's not just an image, right? That will be a little bit disappointing. We can also now, of course, zoom in and see exactly what's going on. So what happens is that the chains can form a ton of connections between complementary DNA by aligning very closely, by forming something that's almost a crystalline structure. This is kind of like when you take a bunch of pencils in your hand and you squeeze, of course, right? It forms something dense packed, almost crystalline. We see that we can even then calculate if there are regions where the bundles cross, what's going on, how much DNA is there. We can also now measure the diffusivity of the DNA throughout this entire complicated material. We can look at the mobility of DNA that is bound to a counter pair. We can look at the diffusivity of DNA that's just not bound at all, or only bound in an individual crossing of two of these polymers, and compare all those things. So that's still purely visual. But what is really interesting is that what you can do in a simulation, where simulation takes off and can do things that experimentally are very hard, is very hard. We say, look, there are basically two things going on. There is a strength of binding of the DNA. If that strength is not strong enough, you don't form a gel at all, obvious, right? The crosslinks are simply, if they're like half a kT, the system doesn't care. But on top of that, you also have to think about how strongly is the DNA bound. And maybe I should explicitly say that because that might not be obvious. Why can the DNA move? Because it's a self-assembled material, right? This is just its micelle. You can simply pull a DNA attached to the peptide out of this self-assembled micelle. It is not that possible. So we can tune that force as well, that potential energy, and that's here. So this is in kT. And we now find out what happens under different conditions. And so we find, well, if you cannot pull DNA with its associated peptide out of a micelle at all, then you just get a gel. This is how any rubber is made, right? So you just are cross-linking a polymer, and there's no way to detach those crosslinks except for breaking them. But breaking them is the other parameter. That's the interpolymer interaction. And so we find that, of course, if everything is too weak, then you also form no gels, because you can just, every crosslink just gets formed and then detached. So both parameters matter, and we really find that the growth rate of these bundles is controlled by both. So that was a science paper a couple of years ago. So I want to show you one more thing, because it's kind of just cool what a simulation can teach you. If you look up close, you see that these things form almost braided structures, right? Kind of cool. And it's weird, because you can easily calculate there's a torsional energy associated with that. That's not good, right? That is an energy that's somehow has to be put into the system. So you think, oh yeah, this is out of equilibrium. It's just wait long enough and it will relax. So okay, if this is out of equilibrium, I can accept that, but it looks also strikingly ordered. You can actually look at these bundles and they have a very regular pitch, not what you expect from something out of equilibrium. So it's low in entropy and high in entropy. That's the opposite of what I would expect. So this looks like a cartoon. It's like a little movie that I'm going to play. It is not a cartoon. It's an actual simulation. So these are two bundles, one covered with blue DNA, the other with red DNA. It's very highly covered in this case. It makes it easier to see things. And they meet under a random angle. And then we simulate the dynamics of what happens if you have something like this. And it zips together in this very regular structure. And it's actually interesting to understand what's happening. For one thing, you see that on the lower left here, there's something going on that doesn't fit. And that's called the chirality defect. So these two chains meet, start twisting around each other, but they make a different choice in terms of helicity, like clockwise or counterclockwise, on one side of the crossing than on the other. It's kind of funny that it happens. The other thing is that you can ask yourself, that pitch, what controls that? And if you look at the movie again, then you will see that the simulation, they get very interesting insights. If you pause it, you see that this opening angle is different from the angle under which they met initially. And I found this really cool analogy to that. If you put on a jacket with a zipper and you zip it up quickly, then you see there's this opening angle, right? You do this every day. And that opening angle is actually controlled by partly the flexibility of the fabric, right? You can align it perfectly, and you can just zip up. But if you zip up very quickly, then the fabric is pulled together while you zip it up, and that's what's going on here. And that controls the pitch of the final twisted pair that you have formed, not the angle that you have initially. Now you may say, well, that cannot be true, because if I had put them in parallel, they would never have zipped. This is true. If the angle is very small, if they're almost parallel, then the initial angle controls the pitch, but that's rare. So it turns out now that we can put in realistic parameters in the simulation, predict that pitch, 165 nanometers. Look at this. I think it was spectacular. So where the simulations really explain what you see parametric. So it's 175 there, nanometer there. And here there's some details that I don't want to dwell on related to the role of DNA coverage on the supramolecular molecules, aggregates, and also the role of the initial pitch. All right, so that's an example of where we are starting to make inroads into like supramolecular assembly. Yes.
May I ask a question?
Of course.
Does the initial angle play a role in the density of twists?
Think about it. Well, I'm thinking of this as the pitch. Isn't the pitch automatically coupled to the, the rate?
Yeah,
Right, it's the same thing actually.
I see.
Yeah. If your pitch is very long, then obviously that is what you would call a twist, right? Right. All right. So I want to talk about another area where simulations don't have to be complicated and yet can give a lot of insight, and that is in dielectric phenomena. So I'd like to start dielectric phenomena with by remembering what we do know about it, right? So if you have a physics class on electromagnetism and you learn about the role of dielectric effects, then you learn about image charges. And on the one hand, that's super cool because it's kind of fun to do. Also not difficult, right? I mean, you can learn it in half an hour, but it's spectacularly powerful. And I just want to remind you of where this comes from, because I only realized that much later in life than I learned the image charges themselves. It comes actually from William Thomson, I don't recognize the name, but that is Lord Kelvin. And he figured this out, and this is the moment when we all should get modest, in 1845. Why do I say that we have to get modest? In 1845, this was a few months after he had turned 21. Okay.
Please don't remind me of how unaccomplished I am.
All of us. I mean, because it gets better, I was reading about it last night. But do I know more about it? I went to Wikipedia and you get this one of these rabbit holes, right? And you realize that his work, not on the on dielectrics, convinced Michael Faraday to investigate this further. And Michael Faraday then discovered the Faraday effect, I think the same year or a year later, which then was the first time that people realized electricity and light are connected. So it's not one of the smaller inventions, right? I think, gosh, so Michael Faraday was maybe not a student there, and then I look at Michael Faraday. Oh no, Michael Faraday was like in his 50s or so. Where do you find if somebody in their 50s being convinced by a 21-year-old to change their research direction and then discover something so fundamental? So this letter to Leoville, like another big name, of course, written by by William Thompson, talks about, hey, I had this idea about solving this complicated many-body effect. Didn't call it many-body effect, but it's about dielectrics. So the problem with the image charge method, there's no problem with it, but it only works in very specific geometries. Flat surfaces. Somebody else may tell you also for spheres, yes. But if the spheres are not metallic, but like dielectric, it's so complicated. It was only done in the 1880s, I think. And then cylinders is another solution, but then the charge has to be in the center of the cylinder, otherwise it gets horribly complicated. So anything else where you have two materials meeting with dielectric mismatch, which is basically the default, right? It would be a coincidence if they have the same permittivity. It gets very, very complicated. And I just want to show this picture. Who did this? Our names came to. This is from a few years ago. There was somebody synthesized these particles. It is two silica spheres that form a dimer, and then something is polymerized around it. You put it in water, you add salt, you put in an electric field. They self-assemble into cool structures. Okay, fine. Think about this now from a perspective where somebody comes to you and says, can you simulate it? Oh my God. So now the silica is charged. Unless you're at the isoelectric point, the silica will be charged. There are ions around, so there's like a very complicated electric field. There's an external electric field. Every interface between any material will be polarized, right? So this is the silica with water, it's the silica with this polymer. And then the electric field itself, of course, is complicated because these ions are also responding to the external electric field. And now you say, okay, do you have a lot of these particles and they form a complicated structure? Please explain. That's, of course, extremely complicated. People have thought about problems like that since the 1970s. It is very obvious what you have to do. You have to essentially put a grid on any surface that you're interested in and solve the Poisson equation on every grid. That has to be done self-consistently because you will, in your process of solving it, will find polarization charge, but as soon as there's a polarization charge at any dot here, right, then this sort of grid-like surface that just points where you solve the Poisson equation. You will develop a charge and say, oh, wait, now there is more charge in the system. I need to recalculate everything at every point again. And so you keep doing that, so it's iterative. So it's a self-consistent calculation. And now you have to combine that with a simulation in which these particles then, in response to these forces, start to move or rotate. And when they have moved a little bit, you have to say, wait, I have to recalculate all the polarization charges. So it gets mind-bogglingly complicated. There's a whole list of people who've tried this. Lots of very smart ideas. I have nothing negative to say about it. But each of these ideas is so slow that you cannot dream of doing a simulation in which the particles then respond and move around and you make a prediction. So I had the good fortune a decade ago to have a postdoc working with me. This is one of those amazing cases where I don't understand how it's possible. Kipton Bowers, he's now a staff member at Los Alamos, and done his undergraduate in computer science, then does a PhD in physics. I do not know how this is possible, how you can actually enter a PhD program with an undergraduate in computer science, but he did, he succeeded, comes to me, and then I realized this guy knows much more about algorithms than I do, right? Because this matrix is not well conditioned. Of course, then I quickly have to look up what that means, and I'm exaggerating a little bit, but he definitely had a much better idea. He said, okay, we have to solve this matrix equation, and I Google it and I download something. He says, no, we have to use this particular method that every computer scientist has learned in their junior year. And so we work together. I point out to him what is interesting science, and he points out to me what is good computation. And so I just want to show you what we found, because it actually has a little nice tail, this story. Because I want to end with something that very focuses on algorithms. But this is like a piece of like physics or physical chemistry. My experience is that if I did a quiz, which I hate doing in seminars, so I will not do this, many people get it wrong. It's like, I never knew this. And then you go back and you realize, I actually learned this as an undergrad, but you forget. I forgot too. Think of a dielectric particle, piece of plastic in air. Take a point charge and I bring it to the surface. You will polarize this sphere. So the dipole moments of the atoms making up this piece of plastic will reorient, and the point close to contact will have a charge that is of the same sign as the charge you bring to the surface. So you induce a repulsion. You have to squeeze harder and harder because the surface will get charged there. If the particle that you bring is negative, the surface will also be negative. So, well, wait, what? How is it possible? You create a charge? No, you just reorienting dipoles. So in this top image, the far side here will be oppositely charged, so that the whole surface is neutral. Okay, so far so good. Just now take the same particle, but I put it in a medium with a high permittivity. Then the opposite happens. So if the particle is not in air, but let's say in water, then something very different happens. So in air, the air has a lower permittivity than the particle, right? You put it in water, then the water has a higher permittivity than the particle. Now you've used an attraction, a very funny asymmetry. So now when you bring the charge to the surface, it actually gets pulled towards the surface. So that effect, you might then realize, that should matter if I put particles together, like positive and negative particles. And should they attract now more in a high permittivity medium and less in a low permittivity medium? So that the degree of bonding should be different and should get maybe even different structures. So we studied that. And that's now where you need a dielectric algorithm that really allows, the process to proceed. Look what we found. First thing, which was really cool, get different structures. It was a huge relief to me because I have been pushing to work on this for a couple of years. It's a boatload of work to program this, to come up with an algorithm to program it. And then, of course, I already in the process had met people who told me when I said I was working on this, they will not matter. They'll be very short-ranged, they'll be very weak. But I persisted, and then we found there is an effect. Right? So the thing is this, with dielectric phenomena, if you look in the literature, most people ignore them for this sort of assembly. And you ask people why. And they say, well, it's very weak. And say, can you explain that? And then you realize it's some sort of conspiracy, right? It's just everybody agrees it is too complicated. So if we all agree that it doesn't matter, then we're all safe. So this was now what we found. It does matter. You get very different structures. So these are the same particles in a different medium. Now, if you're very quick, you might say, hey, if it's a different medium, then all the interactions are of different strength. Absolutely true. But we then change the temperature to get to the same effective strength at contact. And nevertheless, you get a different structure. So get here this FCC structure. Now we make the small and large particles. They are the same in charge in terms of magnitude of the charge, opposite in sign, and different in size. Interesting thing here is that you say, wow, so you get a sodium chloride crystal structure. I could have told you this for positive and negative particles. It's less obvious than you may think. We all learn positive and negative from sodium chloride. Because sodium and chloride have very similar sizes. Nobody tells you that. That's just, taken for granted, and nobody thinks about, well, if the sizes are different, would you get the same thing? It turns out that actually the fact that we get the sodium chloride crystal structure here is surprising. It is due to the polarization effect. If I turn off the polarization effect, it would not form a sodium chloride crystal structure here. Something more like, I think, word-sized crystal structure instead. And this open structure, of course, nobody predicted that. what I want to note is that the open structure here happens in the case where there is strong binding. The dense structure happens where there is weak binding. Right? That's exactly the opposite. Right? What did I miss? It's a nice reminder of many body effects, which is, as I said early on, entropy and also many body effects. That's where human intuition tends to fail. Yes, if you bring one negative charge to a particle, you induce a strong attraction. It's that red area that you see on the white spheres. But now remember, it's not charge that you are creating, you're just reorienting dipoles. If you make that point strongly positive, something else has to become negative. So what happens is, the second blue particle arrives, it doesn't want to sit close to the first one, so it goes to the other side. So imagine now you have a particle on the North Pole and one on the South Pole. But because the whole surface of this white, ping pong ball has to remain neutral, the entire equator now is negatively charged. And you start to repel additional particles. And that's why you get these elongated structures, why it gets so open. Because the equatorial region is no longer attractive to anything else. And so that's something, of course, that when I tell you, say, yeah, it makes sense, but that we had not anticipated. Here, nice example. Nick Kodo from the University of Michigan came to me and I told him this story. He says, we've seen that. And so there's this paper where they make these cadmium telluride nanoparticles that are used them, and they form these nanowires. And because they are nanoparticles, these effects are particularly strong that we discovered. He said, yeah, this is the explanation. And it's fun if you go to the original science paper, which had been published 12 years before we published our work, and you read the paragraph about the reason for these nanowires. It basically starts with mumble, mumble, van der Waals, mumble, mumble, right? It's just a guess. But this is the explanation. I'm not speaking negatively about the paper. He's a very good scientist. But I think in that case, it was just not clear why it happened, and simulations really explain it. Now, I don't know how I'm doing on time. I want to show you one more thing, because it's an example of how simulations, especially if you collaborate with people in mathematics who are interested in this sort of work, can get you even further, to a point where I could not have gotten along. So the scientists, Shanghai Jiaotong, and yet collaborated at New Jersey Institute of Technology, and they said, yeah, we have found a way to extend variation of image charges to systems where there is more than one sphere. And it's very complicated. The code is so complicated, so the algorithm, I should say, is so complicated that it's a full PhD of somebody working on this for several years, right? And then I said, you have to put this in a simulation. I have no idea how to put this into like an existing package, right? We will write our own simple molecular dynamics simulation. That's easier for me than to understand how to take these 10,000 lines of code and somehow match them to an existing package. Because the MD simulation itself, a basic version, is not hard to write. And then the student said to me, oh, so you need forces. Now what? And so he had these formulas, right? And I put him in Mathematica, and you can take a numerical, you can actually take an explicit derivative in Mathematica, so then we have an equation for the force. He wanted to code it. And then now I luckily remembered something from my own PhD. He said, actually, in Mathematica, you can tell it to translate whatever you have into C. And then you can just copy and paste it. It's called C4 or something. And so then you get a code that's completely illegible. Every row is 80 characters, pages and pages, and defines variables with the weirdest names, and say, okay, just don't look at it, just put it in the program. So we did. And what I like about it, this method that I just, described to you before with all the points on the surface, it's beautiful. It works well. I'm excited about it. And if I wanted to be mean, I could say, yes, it's actually an uncontrolled approximation, because you have no idea how the number of grid points matters. The degree of convergence that you use in the self-consistent calculations How much does it matter? We don't know. If you make the calculation of the electrostatics, which goes via so-called Ewald summation, less accurate, can it affect the convergence of what you're doing? All unknowns. So, yes, if I would be unkind, I would say uncontrolled approximation. Who knows? So, this complicated method is 1,000 times more accurate. I confirmed that empirically. Okay, that's impressive. That's cool. While at the same time, 100 times faster. I'm not even sure whether that means it's 100,000 times better or even more than that, right? It's just unclear. It's like a different situation. I mean, you have to understand, if I make something 100 times faster, I go from a simulation that takes a year to a simulation that takes 3 or 4 days, right? So suddenly we can explore things, we can start varying parameters, system particle sizes, particle compositions, and so on. Now you may say, well, why do you even talk about anything else? This is only for spheres. The methods that I describe works for any shape, because any shape can be, filled with or covered with points, right? Mathematician would call this a boundary element method, but it's just grid points on the surface. This method only works for arbitrary combinations of spheres. And just to finish up, I want to show that we actually managed to use this particular example. So this is work on colloids a long time ago, almost 20 years ago. It's very clever in the sense that they take oppositely charged spheres, but also make them fluorescent in different colors. So you can really see the crystal structures. And the cool thing is, because the sizes between the colloids in this case are so different, you can get crystal structures you don't find in nature. Mathematicians have labels for them, but then they cannot be made with atoms because the sort of size ratios do not exist between atoms. And lots of interesting structures, like for example, situations where 4 small particles dot one side of a big sphere and then another sphere comes in, right? So every junction point is surrounded by lots of small particles. And I realized, if you now include dielectrics, polarization, you should get even more crystal structures. But that's hard, and it's now a problem we can address. But only because we have this super fast algorithm. And so here's just an example of what I was telling you earlier. This is the size ratio between, let's say, the positive and negative particles. If that size ratio is small, you always get FCC crystal structure. Always. Even if those particles are polarizable, and when you put them in a low permittivity medium, high permittivity medium. That's a sodium chloride crystal structure. None of this remains true if the positive and negative particles, large and small, have a size ratio that's more than 2. In this case, yes, you get FCC crystal structures if you put them in a very low permittivity background. If you say, I ignore dielectric effects, it actually forms this one-side crystal structure. So that's different. And so then this is where I made the point that if you forget about polarization, but you simply say, I have a binary mixture of positive and negative particles, you do not get sodium chloride if the sizes differ by more than a factor of 2. And you get these very open structures if you are in a high permittivity background. So let's say water or something like that. And then, because we now have this very fast algorithm, we can do long simulations, we can get lots of different structures. I'm not sure I have another slide on that. Yes, here. So for example, here we take a difference in size ratio and a difference in charge ratio. The outcome is really not so important for today. It is more to illustrate to you. This is now so fast that we can just blanket parameter space, make something, have a fun idea and just try it. Because the simulation is done in a few days, whereas before it would be many, many months before you would get anything useful. So here is an example of something that forms this FCC crystal structure, but in a strange way. Lithium bismuth can make it actually, but if you put this in water, you would get these very open structures. Completely different, same particles, right? That's what I want to emphasize. And now we have this also with high reliability because this algorithm is so much more accurate. So in hindsight, we discover that our algorithm, which I jokingly call an uncontrolled approximation, and the old algorithm, apparently did a good job. It found the right structures, and now others since then have seen these open structures as well. So I know we were right, but in the beginning, it was just an algorithm where many of the parameter choices were controlled by what we thought was good enough, what gave us an answer in, less than 3 weeks. So it's rewarding to see that it all worked out. I believe that is my last slide. Oh yeah, I don't have time for this. I will not show you this, but it's more like a project where we wanted to show that just using image charges, which is the simple method, right? You can do a lot of exciting things. And just I will go to my very last slide to give you a flavor of the sort of problems that can be solved. It's here. Polymer brush, right? People making lots of these systems right now, they're dreaming of making a polymer brush in a channel, and then you think, oh, could I somehow make a valve, right? And people are talking about situations where you maybe have an ionic flow, and diodes have been made, but now can we make a transistor in which we have ionic currents? And so then one of the topics that typically comes up is like, maybe we can coat the inside of this channel with polymers or polyelectrolytes, control their conformations, and maybe that way control the ionic flow. And so postdoc Hannah Antilla and the student, Jiaxin Yuan, they came to me and said, well, what if now this polymer is coated on a substrate that has a different permittivity? Now there are tons of complicated dielectric effects. Polymer can expand or contract. The ions will move in a certain way, right? So how do ions move to channels like this? And so that's something that we published a few years ago in ACS Macro Letters. We showed that you can actually control the ionic flow not only by the, let's say, the rate, the density at which the polymers cover the substrate, but also the dielectric constant. So we found this whole sort of like world of dielectrics, lots of surprising phenomena. And this is a simple simulation again, because it's a flat surface, you can just use image charges. This simulation is barely slower than a standard simulation. And I really think that's important or be helpful to bring up in a workshop like this. Like you can make advances, but hasn't been done before. You can find lots of interesting things at an expense that is really modest. Changing your an existing computer program that you download, like LAMPS, to do this takes a few days at most, and most of the time is spent on understanding how the existing code works and where you have to make your changes. And then the simulation is as fast as anything. So this is done in a few days. So lots of openings for exciting investigations of soft matter systems. As you can tell, I'm quite partial to electrostatic interactions. They're important, they're omnipresent, and often give you surprises. So with that, I want to thank you for your attention, and I'll be very happy to answer any questions. Thank you.
Critical work instructions. I'm wondering if you have looked at or considered looking at what happens when you, over the course of the simulation, change the permittivity of your solvents or whatever you're in, so that to the extent the structure is slowly morph into your crystalline structure, or are they locked in place with their form? Does it depend on how quickly the medium is changing?
I don't think that we have not looked at it. I'll be very surprised if they're locked in place, because you realize that if you think of those chains, right, they are kept apart by the fact that the equatorial region is repulsive to any other equatorial region. If you turn that off, there's no reason for them to remain locked in place, right? Everything is completely mobile at the surface. Yes, it has to depend on the rate at which you change things. But I think even if you go to the limit where you do it very quickly, you just turn off all electrostatics, or at least the dielectric part, I'm convinced it will just relax. Yeah, I'm certain. There's no reason I can tell that keeps this kinetically trapped. And in fact, this is electronic polarizability, right? It's actually it has a very high response rate, so it will change very quickly. Yeah. Good point. Yeah.
With the crossing twisting polymers,
Mhm.
you always get exactly one chirality this reversal.
So you mean that any that in one direction there is no reversal, right? Because on the opposite of the crossing side of the crossing point, you can do whatever you want. So I can go clockwise here and clockwise here or counterclockwise here.
Okay.
Yeah, that's actually what that is called the chirality effect. But I would be surprised to find it changing its chirality in one direction coming from a crossing. Right, so if you have two wires, they're semi-flexible that are twisted in a certain direction, and now you stop and say, oh, spontaneously they would start twisting oppositely. That sounds terrible. Yeah, in terms of number of contacts, and also in terms of the bending rigidity. I will be surprised if that were to happen. We have not seen it. Trying to remember what the TEM image showed back there. Yeah, so for us, this is, of course, it's completely regular. Even hard to tell, right? I find it hard to tell even that if it's just regularly twisted. Apparently it is. So I'm not aware of more detailed studies of where some student went to all the images trying to find, something where the chirality changed back. But I do not recall seeing it in the simulations, no. Except for beyond the crossing point, right, to be sure.
Oh.
I want to make sure there's no confusion. Yeah, so let's play this. I know you want to say something, so I will play this while you talk. Yeah. So what did you want to point out?
So you pointed us to this one chirality defect.
Right.
So
Which is here.
yeah, is that generic too?
Oh, I think it's coincidence.
Oh.
I misunderstood. I thought whether there will be more of these. No. It will only occur, I think we agree on this now, at the crossing point. But I think left and right of the crossing point are not correlated. So it does not have to be a chirality. Yeah. Thank you. Yes.
So, with regards to the, interplay between the energy of the DNA coded
Right.
file, being able to bind to each other versus being stuck in
Right.
a structure. Did you look at whether or not the coded molecules can move within the micelle? How the energy of binding there might relate to those kinetics, and if that rate is comparable to the
It's a very good question. I'm just quiet because I'm trying to remember exactly how we did not have that. I think our DNA could bind to another DNA within a certain distance, and it could disconnect from the chain altogether. I don't think we allow translation of the DNA along the chain. But I do agree with you that it might happen. That's why I'm quiet. It's so obvious to me also that it might happen that I wonder whether we actually just allowed it or not. And I honestly don't remember for certain. I don't want to say the wrong thing. It is, yeah, that could happen. The question is, what would it change, right? If you allow that.
I'm curious if the rate of that motion, if that time scale is comparable to.
I see.
Change like this, strength of interaction between two chains on.
Right, I see now, I see. Because I was thinking about the other structures, I was thinking, well, we don't know anything about those rates anyway, and just found, the bundles. In this case, we did not allow it to be mobile. In the particular movie that you see here, it's fully covered, so then it also doesn't matter. But on the next slide, I think I talked about No, yeah, so this is. It's irregular, so I wonder why it is. I don't remember that, it's on the answer. But the problem I see is that if I were interested in this, I have no information about the rate at which this peptide can, with the DNA attached to it, can migrate through the micelle versus the rate at which this whole micelle can bend and translate through the solvent. So then it becomes a bit of a guesswork, right? You can then do something and you're very excited, and then the reviewer says, well, where did these weights come from? He says, well, they were random, and it was not a very good answer. So it's a nice thought, but I really don't know how to realize it in a way that's convincing. Yeah, interesting.
Probably not without allowing the strands to be in flesh.
Well, so it's very simple, right? The simulation, it's just the DNA is attached. Yeah, I did have to hop too. That's the other thing. That's now I know for certain that we don't allow it. Yes, thank you. That makes me realize it. They are attached to the centers of spheres. Those spheres are rigidly bonded. I'm convinced that we did not make the DNA hop. Well, then what do you do if there's already a charge on a neighboring sphere? So no, we explicitly did not allow this in the simulation. I realize now. Yeah.
Do you think it's like work process?
Hope not. I mean, in hindsight, I can say, which is not a strong response, I realize, not allowing it still makes us see the same structures, making me feel that we have uncovered the mechanism. Also, there's one thing. There's one thing that I think helps me here. So I showed you this image, right? Here. And I acknowledged, so this the degree of purple pink gives you an indication of where the DNA is. But then I also acknowledged this was Photoshop. So how do we know? Here you see the actual images. So now the red is actually indicating the DNA. So you unambiguously see that the DNA has segregated. So we know it's not just merely motion of DNA along chains. The DNA really comes out with the attached covalently bonded peptide and goes into another micelle. So in that sense, I feel pretty good about the way we model it. Yes, thank you for reminding me. Right?
Really nice. So I in the same system, I had a question. So I was curious if just like in DNA, you can simulate the system to have, let's say, like a tension, observe phenomena like supercoiling.
For this particular system, yes, you could, but then the burden is a little bit on me to motivate that, right? Because it's not observed. These things are big, right, and stiff. Nobody sees anything like supercoiling of them. It's also almost like a bit of a contrived system at first sight, like why make this? I did not address that, but it actually has fantastic applications. These supramolecular gels are used in amazing advances in medicine, like the ability to actually reverse damage to spinal cord injuries, which is spectacular. Right. So when there is like a wound, either spinal cord or traumatic brain injury, then these gels get injected, and apparently the response of these gels to certain biological cells, sorry, these gels to cells is unique. So that's why these people did experiments were interested in it, right? So they don't see anything that is like supercoiling. They are not interested in it. So then I really have no reason to say, oh, could we, do a simulation in which we see this? People have definitely done work like that in simple polyelectrolyte models. So let's say for DNA, where you take semi-flexible charged chain, and you see if that forms a compact structure by let's say, adding multivalent ions. So multivalent ions make polyelectrolytes aggregate. DNA is well known since a long time that if you add bivalent salt, the DNA precipitates out of solution. And if those chains are semi-flexible, you indeed get coils, at least. That's the very least that people have done. Simulation becomes slow when you have these compact structures, right? Because now everything is strongly bound and multiple KT per bond. So whether people really see supercoiling, I don't know for sure.
I mean, yeah, like not necessarily this, but I'm sure studies like this could motivate like understanding how DNA holds around, let's say, like stones and all that.
Right, people have done that for sure. Yes. And then you take a much simpler model. It's called the bead spring model. You simply have a particle that's charged, there's a bond, charge, charge. That is a standard model that people use. If you do true atomistic DNA, it's terrible. It will be very short, what you can do. I worked with another student on some intermediate model, which is like semi-realistic. And then you can actually simulate siRNA, so small interfering RNA. But that's only like, I don't know how long it is, maybe 20 nanometers or something. That's possible. But if you see the persistence length of double-stranded DNA is 50 nanometers, right? So then to see things like coiling, etc., or like see it wrap around histone, it would take a very large system. So you need a simplified model. People have done that. Yeah, I think already like in the last 20 years, people have done a lot of work on that. No more questions?
More questions? We're way over time.
Okay.
Yeah, let's take Erik. Thank you. Let's take like a 3-minute break while Michael sets up and then we continue, okay?
Is it just me or do the DNA images look like Jackson Pollock pages?
Yes, I've heard that comment before. Yes, yeah.
Oh, I'm glad to know that this is not an original fact.
Very interested in